Hello, welcome to this new video. So in this video, we are going to have a look at how we can save and load train deep learning models using PyTorch. So if you have seen our previous two videos, we have explored how we can do the same when we train a machine learning model using scikit-learn. There we used Pickle and Joblib to save and load models. Then we moved ahead with TensorFlow, where we saved it in .h5 format, then .keras format, and then the saved model format as well. Then there we built a Gradio app to load the model to see how you can load a model in a production setting or a deployment scenario, and use that particular model for inferencing. So here in the PyTorch, what we are going to do is that we are again going to see how what are the different ways we can do the same using PyTorch as well. So first, let us have a look at the imports. So we are just importing the required imports from PyTorch, such as the PyTorch itself, then the neural network module, then the optimizer module, and the data set and the data loader module as well. And for the dataset, here we are going to use the same TensorFlow dataset which we have used in the previous video as well. And because we are building the same Gradio app, we are importing that and NumPy as well for array processing. Then we move ahead with the configuration or the set of standard variables which we are going to need in this particular code. So if you remember in our TensorFlow video, we did the same thing where we defined the vocab size and the max length, but here we are defining additional parameters. So the additional parameters here are nothing but to build the model which we are going to build using the PyTorch, such as the embedding dimension, hidden dimension, what needs to be the batch size, number of epochs we need to train, and then the device. So one of the major difference between TensorFlow and PyTorch is that TensorFlow gives you a very high level API that helps you write code in much fewer lines as compared to PyTorch. So in PyTorch, you need to handle things manually by yourself. So that is the reason we have to define whether we are actually using a GPU or not. So in my case, because I want to use a GPU, I have to find out whether GPU is available. If available, then shift to GPU, or else then stick to CPU. So this is a standard line of code which we use in pretty much all PyTorch training loops. Next, we load the dataset similar to how we did in the TensorFlow library. Then we move ahead with building the dataset class. So in the TensorFlow code, if you see, we will not have defined any dataset class because, as I said earlier, TensorFlow provides very high level APIs that makes number of lines of code we need to write much smaller. But because in the case of PyTorch, we need to handle things manually, we will have to define our own class. So here, if you see, we just used the a dataset class which we imported from PyTorch and defined what are the actual data and what is the target variables here, and how to access those from the given files. Um, then we use the data loader class to load the dataset class which we have just defined, and give it other parameters such as batch size, etc. And for the training loader, we are also giving an additional parameter called as shuffle equal to true to make sure we are shuffling the dataset and not going in a sequential manner. Then we build the by LSTM classify model similar to how we did in the TensorFlow code. So first we define the embedding layer, then the LSTM layer, which is bidirectional, then two linear layers to process the inputs from the LSTM layer, and then final output layer, which is nothing but the sigmoid activation function. So here we define what the flow needs to be. So as we get the input, we generally use the forward function to again define the flow of that particular model after defining the layers. Unlike a TensorFlow where we sequentially define each layer, here we can define in whatever format, and in the forward function we determine how the data needs to be passed on from one layer to another. So in the forward function, we get the input as x, then we pass on that input x to the first embedding layer, get the output, then pass that embedding output to the LSTM layer, we get the hidden values, then use those hidden values and pass it on to the fully connected layer and get the output. Then using the same output, pass it on to the second fully connected layer, get the output, pass it through the sigmoid activation function for us to get the classified results and the probabilities. Once we define the model, then we are going to load the model by defining the vocab size, embedding dimension, hidden dimension, and what device it needs to run on. Then we define the loss function here. So because this is a standard binary classification problem, we are going with binary cross entropy loss, and the optimizer which we are going to go ahead with is the Adam optimizer. When defining an Adam optimizer, we have to pass in the model parameters for it to know where the model parameters are stored and what the parameters are. This is the how generally we load a model. So this step in TensorFlow is typically done when we use model.compile function in TensorFlow. Then we come on to the training loop. So if you remember in the TensorFlow code, we would have just used the fit function to run the training part. But here we will have to manually define the training loop ourselves. So here we define some parameters which we need for early stopping. Then we move on with the training loop. So we just loop through each epoch, and then we put the model in the training mode, pass on each batch of data to the model, set the gradient to be 0, then calculate the loss, then calculate the gradient, and then apply the gradient using the optimizer, and then store the loss, and then we also calculate the accuracy for it in each loop and store it in respective variables. Then after the training part, one epoch of training is completed, we run the validation loop as well. So for that we set the model to evaluation mode, thereby we ensure the model weights are not updated. Then do the same thing as we did for training, and calculate the loss and accuracy for the validation as well, and then we are just printing it over here. Then we are also adding a early stopping logic into the code, whereby we check monitor for if whether the validation loss is actually decreasing or not, and if it is not decreasing, we are stopping it after two epochs. So this is the training epoch which we have run. So if you see here, up till epoch 6, the validation loss was actually decreasing, and then from 6th and 7th epoch, the validation loss was not actually decreasing, so it was better to stop the training here. So that's what our early stopping code helped us with. So once we train the model, now we come to saving the model. So if you see here, when saving the model, we have multiple ways of saving the model. So one is called as saving the dictionary of the model. That is nothing but the weights and the other parameters which we have trained the model on. We are just going to save that part, not the whole model as a itself. So in order to do that, we just have to do model.save, then pass on the dictionary or state of the particular model into a .pt file. So in the case of Tensor or PyTorch, whatever model you are going to save, the format or the extension of the file is going to be .pt in that particular case. So that is why we have saved it as model.pt. Then similar to how we can store the entire model itself including in a compiled format, we have an option called as JIT format. So we can also save it in that format if we want. So torch dot jit dot trace, we can pass in the model and all the other input parameters which we need to build the model as well. Then we can save it in a completed format. So this scripted format we generally don't prefer, because again, whenever we are saving the whole model as an including the layers code which we have compiled, the issue is that whenever let us say in later changes, PyTorch changes some of it layer definition or some kind of API which we are previously using, this will break. But instead, if you just save the weight of the model, we can recompile the model using the new API and just assign the current trained weights to that particular model. That way we can ensure that even though PyTorch changes its API, our trained model is not affected. Next we move on to like building the pipeline for the inference part after saving the model. So here we do similarly have the same code which we had in the TensorFlow as well. for tokenizing the inputs. Then two similar functions of encoding the particular review or text input, and then the predicting the sentiment, where we are actually passing in the model as well. So in order to let us say load the model, what we do is that we just load it using uh, first we come load the class. Then after loading the class, what we do is that new model dot load dict torch dot load model save dot pt. So we call in the class of the model, then load the state, use the load state function within the model and pass on the saved load state which we have, and then build the model in the code. So this is how we generally load the model in PyTorch. So once we load this particular model, we can pass it on to the predict sentiment and pass in the input text and get the output as we want it. Then we move ahead with a similar gradient interface that we have built for the TensorFlow as well, and launch our app. So if you see, this is the gradient interface, and let us say if I type in the movie review, so it will just run it on the particular model and give us the output. So if you see here, it gives us the positive output. So this is how we can save and load models in PyTorch. So hope you got a better understanding of how we can save the load models in multiple different libraries, TensorFlow, Scikit-learn, and PyTorch, and how to use that for inferencing as well. So that's it for this particular video. And again, if you have any doubts, feel free to contact us at contact@codersarts.com, or reach out to us through any of our socials as well, or leave a comment in this particular video. And also don't forget to like, share, and subscribe. So see you in the next video.